All right, it's 8, so let's begin. Today we're going to be talking about effective values for periodic waveforms, in particular current and voltage signals. And then from that discussion, we will lead into the concept of complex power. Okay. So let me ask you guys a question. Is the average power absorbed by, let's say, a resistor, the product of the average voltage across the resistor and the average current flowing through the resistor? Raise your hand if you say the answer is yes. So over half of you. We mathematically proved that that's not true Friday. Right? So what I just posited is the average equal to the average times I average. And on Friday, we learned that the average power delivered to a resistor is given by 1/2 the magnitude of the voltage times the magnitude of the current. What's the average value? Zero. What's the average value of the current in a sinusoidal steady state system? Also 0. So how can 0 times 0 equal something that isn't 0? It obviously cannot, okay? So what we are going to learn about are effective values, which is really just an engineering approach to try to make that intuitive thing. Why shouldn't the average value of the voltage and the average value of the current equal the average value of the power? We're going to try to make that work by using what are called effective or RMS values. Okay. So another way that RMS values are used is to characterize signals. So there are probably 40 outlets in this room, thereabouts. There's strips all along the walls and all that kind of good stuff. What is the voltage that's supplied by any of these receptacles in this room? 120 volts, okay? So because you say it's 120 volts, do you mean specifically that it's 120 volts DC? So 120 volts AC, also not correct. See, we're messing with your preconceived notions of things. I'm baiting you guys today, all right? So it is colloquially known that the voltage that's output by one of these outlets is 120 volts. That is actually the effective value of the voltage waveform. So if we have an outlet, I'm going to draw a terrible picture here. Looks something like this. Okay. Typically speaking, this pin on the bottom is our ground pin. And it doesn't look like ground well enough to me. Then over here, we have our neutral wire. And over here, we have our hot wire. And there is some between those two pins, how we power everything, right? So I'm going to call this V of t, and the effective value of V of t is 120 volts, what I'm going to call RMS, where RMS stands for root mean squared, and we're going to talk about what that means in just a moment. So if we got an oscilloscope, we have several around the room, and we jammed scope probes into our outlet, what we would actually see is that we would have 120 times the square root of 2 cosine 120 pi t plus some phase angle theta v volts. That depends on when we started measuring things. Might be slightly off from 120 square root of 2, depending on how many resistive losses and things like that we see down the line, but it's going to look something like that general form. That is a long thing to have to tell everyone, okay? Contains a lot of information that really isn't necessary for the overwhelming majority of power calculations and things like that that we would need. So over time, electrical engineers developed the concept of effective values to condense down the important parts of the information, okay? So let's consider a resistor. Okay. Through which there is some current I of t flowing and some voltage V of t across it. We know that the instantaneous power absorbed by this resistor is simply the product of V and I, but this could also be written as V squared over R or I squared times R, thanks to Ohm's law, okay? So the effective value of a voltage waveform is the amount of voltage that provides the exact same amount of power to this resistor R as the periodic voltage does. And similarly, an effective value for current is the DC value that provides the exact same amount of power as our periodic current does. Mason. The effective value is not an AC voltage. It is a DC equivalent voltage or current that provides the exact same amount of power as the time varying voltage. Okay. So we know that in a DC circuit, the average power should simply be our DC voltage squared divided by our resistance, or down here, our DC current squared times the resistance. In an AC circuit, our average power will, by definition, be the average value of the power relationship. So as we discussed yesterday or Friday, the average value of a periodic function is given by the integral over one period of the periodic function divided by the duration of the period, which in this case is going to look like V squared over R dt. And down here, in terms of current, we're going to have I squared times R. So what we're going to do now is we are just going to set these equations equal to each other and solve for the DC value. And that will give us the effective value of our system, of our waveform. Yes?
Subscript on that I squared. That's what R would be.
DC. So if we say that V effective which is the DC value that we're solving for, squared divided by R is equal to 1 over T times the integral from 0 to T of V squared over R dt, we can observe something interesting right from the jump. The value of the resistor that we're finding the power absorbed by doesn't actually matter. And now it's pretty trivial to figure out what the effective value of the periodic voltage waveform is. We can say that V effective is equal to the square root of the average value of the voltage squared. And we'll often call this volts RMS, where RMS stands for root mean squared. And it literally tells us the mathematical operation that we do to get the effective value. We take the square root of the arithmetic mean or average of the square of the voltage, so RMS, okay? We can do a very similar derivation for currents. So if we have I effective squared times R is equal to 1 over T times the integral over 1 period of I squared R times dt. Once again, we see the resistance value doesn't actually matter. And from this, we find that effective value of our current waveform is 1 over square root of 1 over T times the integral of I squared T. And we might also call this IRMS. So it's effectively the exact same expression, except that when we want a current, we square a current waveform. And we want an effective value for voltage, we square the voltage waveform. Okay. So let's take a few moments here to determine the effective values of a couple of waveforms. So let's start with a piecewise voltage waveform. Let's say that our voltage is measured in volts and our time is measured in seconds for the sake of argument. And we have a repeated sequence of these odd shaped waveforms. Let's call this 2, 5, 6, 8, etc. And we want to determine, and let's call this 10 volts, our peak value. And we want to determine the effective value of this waveform. Is it periodic? Yes. What is the period? 6 seconds. So T is equal to 6 seconds. So in order to find our effective value for this voltage, we'll have V effective is equal to the square root of 1 over 6 seconds times, and because we have a piecewise function, we're going to have to split our integral up into 3 different parts here. So I'm going to integrate from 0 to 2, whatever this voltage is squared. I'm going to integrate from 2 to 5, whatever that voltage is, squared. And then I'm going to integrate from 5 to 6, whatever that voltage is, squared. And now I'm integrating over the entire period of the function. So anytime we have a piecewise function, we need to make sure that we break our integral up into parts that constitutes one full period of the waveform. So now let's fill in some stuff here. So over the interval from 5 to 6, what's the value of our voltage? 0. So obviously, this bit isn't going to actually contribute anything. What about from the interval 2 to 5? It's constant 10 volts. We'll take care of that mathematically in a moment. What about from 0 to 2? So it is 5 volts per second times time, quantity squared. We have a slope of positive 5, having units of volts per second, multiplied by our time. All of this goes underneath square root sign. Okay. So now we're going to do a little bit of math. So we're going to have the integral from 0 to 2 seconds of 25 volts squared per second squared t squared dt plus the integral from 2 seconds to 5 seconds of 100 volts squared dt, like so. I'm going to move the 25 volts squared per second squared out. What happens when I integrate t squared dt? What's the integral of t squared? 1/3 t cubed. There we go. This is going to be evaluated at 2 seconds and 0 seconds. And then over here, we're going to have 100 volts squared pulled out. What do I get when I integrate dt? T. Evaluated at 5 seconds, 2 seconds. So we're going to have 1/6 seconds times 25 volts squared per second squared times 1/3. 2 seconds cubed is going to be 8 seconds cubed minus 0 seconds cubed. And then over here, we're going to have 100 volts squared times 5 seconds minus 2 seconds. Close that off. Trying to pay attention to the units here. So my 25 volts squared per second squared multiplied by something in seconds cubed is going to give me volts squared seconds, right? Same thing on that right-hand bit. I have 100 volts squared times effectively 3 seconds is going to give me something measured in volts squared seconds. And then I'm going to multiply that thing by 1/6 seconds, giving me units of just volts squared underneath the square root sign. Okay. So I have 1/6 seconds. So let's see, 25 times 8 is 200. and then over 3. And then I have, so volt squared second there. Yeah, just making sure I've got everything correct there. And then I'm going to have 100 times 3, so 300 volt squared seconds. One over 6s, or 1/6 seconds. So let's see, 1100 over 3 volt squared per second. Excuse me, volt squared times seconds. And this is going to look like 1100 volt squared seconds over 18 seconds. I'm going to use my calculator because I can't do 1100 over 18 in my head. Sorry, what was that? Okay. Let's see, square root of 1100 over 18. Yeah, 5/3 squared is 22. Volts RMS, or 7.817 and some change. Volts RMS, where we use the units volts RMS to designate that we have the effective value of a periodic waveform. Okay, so anytime you see the units volts RMS or amps RMS, that means that you are dealing with an effective value. So we call this voltage from this receptacle 120 volts RMS if we want to be explicit about things. Jonathan, how may I help you?
It's always going to go down to seconds. Like, the units always go down to seconds.
The units have to go down to volts squared or amps squared here before we take the square root, because we're expecting the effective value of a voltage waveform should be a voltage. The effective value of a current waveform should be a current. Yeah. All right. So mathematically, we hopefully understand how to apply this equation and all that kind of good stuff. I worked this problem in particular because I'm expecting you guys to be able to duplicate something like this on your homeworks and on your exams and all of that kind of stuff. Now, let's tie things back to steady state sinusoidal analysis, which is really the purpose of what we're doing in this section of the class. Okay. So let's see that we have a current waveform, I of t, is of the generic form Im cosine omega t plus some phase angle theta I. What's the period of this waveform? Pardon? Omega is the angular frequency, which is related to the period, but it is not the period. Not quite. So let's draw a picture. Here is I of t measured in amps. Here is t measured in seconds. I'm going to draw this as if the phase angle were 0, just because I am lazy. Okay. So the period t is the amount of time that it takes for this signal to undergo one full cycle. Okay. The angular frequency, omega, tells us how many angles we go per cycle, right? So it's radians in a specific amount of time. 1 over t is the linear frequency f, and omega is simply 2 pi times the linear frequency. We covered all of this in the sinusoidal review thing several days ago. So using a trivial amount of math, we can see that omega is equal to 2 pi over capital T, and therefore T is equal to 2 pi over omega. Everybody okay with that level of? All right, so now we're going to find the effective value. So I effective is going to be the integral, there's going to be the square root of 1 over the period. So that is going to be omega over 2 pi. That's 1 over t times the integral from 0 to 2 pi over omega of our current waveform squared. Our current waveform squared is going to look like 1/2 Im squared plus 1/2 Im squared cosine twice omega t plus twice theta I t. I'm using that exact same trig identity that I used on Friday. It allows me to multiply two cosine functions together. You get 1/2 the magnitude. So let me just write down the trig identity. I'm going to screw it up if I'm trying to explain it like that. So cosine angle 1 times cosine angle 2 is equal to 1/2 cosine angle 1 minus angle 2 plus 1/2 cosine angle 1 plus angle 2. If I multiply both sides by a magnitude there, I'm going to get this result. And angle 1 and angle 2 are literally the same thing, which is why I get a cosine of 0 term or 1 here, and here I'm just doubling the angle. Okay. So much like we did in class on Friday, let's break this into two parts. Let's focus on the right-hand side first. So this right-hand bit is oscillating at an angular frequency of twice omega. So it is an integer. Let me rephrase this. What does the period of this part look like as compared to I of t? So if I were to plot this part right here that I've underlined, since its angular frequency is twice as large, it is oscillating twice as quickly. So normalizing the magnitudes, we'd have something like this. So what happens when I integrate? over this duration t. This area plus this area plus this area plus this area plus this area has to equal what? 0, because I'm integrating over an integer number of periods. Anytime I integrate a sinusoid over an integer number of periods, the answer is going to be 0. So once again, we see that this whole term goes away. So what are we left with? Square root of omega over 2 pi. I'm going to take 1/2 Im squared out because it's a constant. Times the integral from 0 to 2 pi over omega dt. What's the integral of dt from 0 to 2 pi over omega? 2 pi over omega. So effectively, this integral and this part here cancel each other out. And what I'm left with is the magnitude of our current waveform divided by the square root of 2. So we did not use any specific value for the magnitude, any specific value for the angular frequency, or any specific value for the phase angle, right? So the effective value of a sinusoidal waveform is actually independent of angular frequency and phase angle. It only depends on the magnitude of the waveform, which makes the job of an electrical engineer much, much easier, because it doesn't matter if you're here in the United States, where we deal with linear frequencies of 60 hertz in our transmission and distribution systems, or if we're in Europe, where they deal with 50 hertz in their transmission and distribution systems, or in Japan, where they use both, depending on what side of a river they're on. Totally true. The effective value of a sinusoid is always just the magnitude of the sinusoid divided by the square root of 2. Okay. Now, why this is particularly great is if we look at our average power, we found that to be 1/2 Vm Im cosine theta v minus theta I. Found that in class on Friday. I can say that 1/2 Vm times Im is just the Vm over the square root of 2 times Im over the square root of 2 cosine theta v minus theta I, which is nothing more than the product of the effective voltage times the effective current cosine theta v minus theta I. So I get rid of that annoying 1/2 factor that got carried around all over the place when I was multiplying sinusoids together. Using effective values gets rid of it. All right, so before we move on into complex power, which this is a critical relationship, so I'm going to put a box around it, I want to introduce one more domain that we are going to analyze circuits in. So if we have a voltage waveform, V of t, of the form Vm cosine omega t plus theta v volts, or current waveform of the form Im cosine omega t plus theta I amps, we know that these are time domain signals, right? We can convert into the frequency domain by replacing these time domain signals with phasors, where that would be V, our voltage phasor, is just Vm angle theta V, and our phasor current is I is equal Im angle theta I. Our last domain that we are going to analyze circuits in is the RMS phasor domain. So I'm going to call an RMS phasor. It's going to have a slightly different notation than our regular frequency domain phasor. Instead of a bar over it, I am going to put a tilde over it to let us know that we're in the RMS domain. And by definition, our RMS domain phasors is simply our voltage, or excuse me, our frequency domain phasor divided by the square root of 2. So we're going from the frequency domain to the RMS phasor domain by using effective values instead of the magnitude of our signals. So this is going to be Vm over root 2 angle theta V, or V effective angle theta V. And similarly for currents, we have Im over root 2 angle theta I, which is simply I effective angle theta I. Okay. Brody, do you have a question? Okay. So now let's introduce the concept of complex power. So we learned moments ago that average power can be expressed as V effective times I effective cosine theta V minus theta I. How can we express this in terms of our RMS phasors?
Our magnitudes added together, or our magnitudes multiplied for magnitude, and our angles subtracted for the angle.
So,
like we just take this, make one big phasor out of it.
kind of, okay. So let's look at something here just really quickly. You actually don't need to write this part down because there's intentionally going to be a mistake in this part, or not really a mistake, but not what we actually want. So if I have the product of the RMS phasor voltage and the RMS phasor current, what I would have is V effective, excuse me, angle theta V multiplied by I effective angle theta I. Give me just a second to save this and restart, or it's going to keep giving me that error and annoy me to no end. So I would have V effective times I effective with an angle of theta V plus theta I. That's something pretty close. If I wanted to have theta V minus theta I, what should I do? Anybody remember how we can manipulate complex numbers, specifically changing the sign on the angle? Pardon? I want a mathematical operation. So actually adding 180 degrees doesn't change the sign on the angle so much as it changes the sign on the magnitude. What does the complex conjugate operation do? You guys supposedly took notes like a week ago. Jake, you mumbled something. What was it that you mumbled? Yes. So the complex conjugate operation literally changes the sign on the angle only. So if I had V RMS phasor times I RMS phasor conjugate, that would put a negative sign there, which would in turn put a negative sign here. So I have theta V minus theta I. Now, our average power is just the real part of the effective, I effective angle, theta V minus theta I, or it is the real part of the product of the RMS phasor voltage and the conjugate of the RMS phasor current. We call this operation RMS phasor voltage times the conjugate of the RMS phasor current. Complex power. Complex power is a quantity that is used by power engineers to succinctly characterize the power absorbed by a given load in a steady state sinusoidal circuit. It is a very powerful quantity in steady state sinusoidal power analysis because it contains all of the information pertaining to the power absorbed by a given load. Okay. So we are going to define our complex power as S. It is equal to simply the product of the RMS phasor voltage across whatever we're interested in finding the power of times the complex conjugate of the current flowing through whatever we're trying to find the power of, okay? So we have dimensionally volts RMS, which is just voltage, multiplied by amps RMS, just amps. So the units of the complex power are volts times amps, okay? what we've dealt with up to this point, we've called that watts. Well, watts is what's used for the average power or the real portion of the complex power, okay? So we give complex power a special unit called the volt ampere. Dimensionally, it is the exact same thing as a watt, but whenever you hear volt amperes, you know that you're dealing with complex power. So how many of you guys have ever bought a generator? Probably not a whole heck of a lot of you. Some of you may have purchased UPSs for your computers and things like that. And on the box, it probably says something like it's rated for 1800 watts, 2300 VA. That VA is the complex power that it is rated for. Okay. Effectively, it tells you, well, we'll get into why there's a difference in those numbers in just a moment. But anyway, it's something that some of you may have seen at some point, okay? All right, so since our complex power is simply the product of two complex numbers, it will obviously also be a complex number, meaning that we can represent it in a rectangular form or a polar form. So let's start with the rectangular form. This is going to be V effective, I effective, cosine theta V minus theta I plus J V effective, I effective, sine theta V minus theta I. So let's call this part right here the real part of the complex power, the average power, because it's what we've been calling it all along. Why would we change? So this is P average, which is the average power, and it is measured in watts. The average power represents the portion of the complex power that is capable of performing work on a load. Okay, so this is what effectively gets converted to heat in electromechanical systems. This part over here, the imaginary part, is what we're going to call Q, the reactive power. Reactive power is measured in VARs, volt amperes reactive. And what the reactive power represents is the temporary energy storage capacity of the system, okay? So resistance contributes to average power, capacitance and inductance contributes to the reactive power. And when you add those two parts together, you get the complex power. And we're going to show that graphically in a few moments using what's called the power triangle, which is something that's going to tie all these relationships together, because you're about to get hit with a ton of equations, none of which I actually expect you to memorize. It's all buried inside a simple graphical tool that your calculator can easily interpret, okay? So this is the rectangular form of the complex power. Now, let's look at the polar form. Okay. So we have simply V effective times I effective angle theta V minus theta I. So the product of the effective values is simply the magnitude of the complex power. And this has a special name called apparent power. The apparent power you can think of as kind of a worst case scenario. And by that, I mean, it's simply the effective value of the voltage multiplied by the effective value of the current. There is no potential cancellation of anything because of a difference in phase angle. They're both at their absolute maximum value. And so this is the most power that could be delivered or the most power that could be absorbed by this particular load, okay? Not taking into account any phase difference between voltage and current that would lead to other things happening, okay? Since it's simply the magnitude of the complex power and the complex power is measured in volt amperes, the apparent power must also be measured in volt amperes. And then we have the difference of our angles. This we're just going to call theta S. And it also has a special name. Our power factor angle. So let's talk about our power triangle before we talk about power factor. So for a generic impedance, here's our real axis, and here is our imaginary axis. Let's say that we have some complex power S. The projection of S onto the real axis is simply the average power. The projection of S onto the imaginary axis, the reactive power. The magnitude of S is the apparent power, and the angle formed between S and the real axis is the power factor angle. So effectively, we can say that S, our complex power, which is nothing more than the product of our RMS phasor voltage and the complex conjugate of our RMS phasor current, can be written as P average plus JQ, or the apparent power angle, the power factor angle. This is why I tell you guys you don't really need to memorize all of these equations. If you can do this mathematical operation and then make your calculator give you the answer in both polar and rectangular form, you know everything there is to know without having to memorize a single equation. The real part is always the average power. The imaginary part is always the reactive power. The magnitude is the apparent power, and the angle is the power factor angle. No need to memorize all the equations that I wrote up there. Doesn't hurt, obviously, but it isn't remotely necessary. All right. There are a few things that we can glean off of this power triangle as well, but we'll revisit that after we talk about the concept of power factor. So the power factor of a particular load is hopefully obviously related to that power factor angle theta s. So we can define the power factor as simply the cosine of theta s, and using basic trig identities on our power triangle, this comes out to be the ratio of the average power to the apparent power. The power factor at which an electrical element or network operates at is a measure of the efficiency of power transmission to or from the network. So effectively, since cosine ranges from +1 to -1, +1 represents 100% efficiency of absorption. -1 represents 100% efficiency of supplying power, and everything in between is some level of inefficiency due to the presence of either capacitive elements or inductive elements, okay? So if 0 is less than theta s is less than 180 degrees, we say that our power factor is lagging. And when -180 degrees is less than theta s is less than 0 degrees, we say that our power factor is leading. So if theta s is between 0 and 180 degrees, what does that mean? That means theta, yes. Sorry, yes, leading. Thank you. Lagging for both doesn't make any damn sense. Thank you very much. Thomas, was that why you were raising your hand as well? Thank you. So if theta s is effectively positive, what does that imply? Well, theta v is larger than theta I. Okay. Another way to think about that is that the current must be lagging the voltage in order for that to happen. Similarly, if theta s is negative, then that means that theta v is less than theta I, or the current is leading the voltage. So that's where these comes from. Power factor is related to whether or not the current is leading or lagging the voltage by the angle theta I, or theta s, okay? So a couple of things to point out here. If theta s is equal to plus or minus 180 degrees, we consider this to be neither leading or lagging. That's because we're operating at 100% efficiency. So there is no phase difference, or they're exactly 180 degrees out of phase, which means effectively there's no phase difference, just the magnitudes are different. Okay. If theta s is equal to plus or minus 90 degrees, we also have neither leading or lagging. I missed the or there. And that is because, damn it, it's going to do it again. So 90 degrees out of phase effectively means that we are operating at 0% efficiency. Our system is completely inductive or completely capacitive. Any energy that is absorbed in a half cycle of our sinusoidal system gets supplied back to the system in the succeeding half cycle. And it's just transferring energy back and forth, back and forth. There's never any opportunity for energy to do actual mechanical work. So 0% efficiency. Okay. All right. So what do I want to talk about now? You guys are getting restless because I've been ranting for an hour. So let's get close to wrapping things up here, okay? I want to talk about alternative relationships here really briefly. Close, reopen. No. All right, so these alternative relationships for complex power are very similar to the alternative relationships for instantaneous power that we developed on Friday. Effectively, it's a shorter way of figuring out complex power for resistors, capacitors, and inductors, where we won't need to know both the voltage and the current RMS phasor values. We'll only need to know one of those pieces of information in order to determine the complex power, okay? So these relationships arise because, unsurprisingly, Ohm's law in the RMS phasor domain is Ohm's law in the in the phasor domain is Ohm's law, in the time domain is Ohm's law, because Ohm's law is always Ohm's law. That's why it's a law, right? Hopefully this makes a lot of sense. If we wanted to get this to this version of Ohm's law to what we have in the frequency domain, we would simply multiply both sides by the square root of 2, right? So if we use this relationship and the relationship that our complex power is equal to V times I conjugate, what we'll find is, in general, S is equal to, so let's substitute V as I times Z, and then we multiply by I conjugate. So this looks like I conjugate times I times Z. What's I conjugate times I? So I heard the real portion. I disagree. What did you say, Ethan? Okay, so it's not the real part. So let's scroll down here and figure it out. So if I have a complex number A that is equal to the magnitude of A angle theta A, then A conjugate is going to be the magnitude of A angle negative theta A, right? So A conjugate times A is going to be the magnitude of A times the magnitude of A with an angle of theta A minus theta A. Magnitude squared. So this will just be the effective value of the current magnitude squared times the impedance. Okay. Let me erase this stuff down here. We don't need it now that we know how that works. Similarly, I could say that I'm going to have V multiplied by V over Z conjugate, just using Ohm's law, which is going to look like V conjugate times V over Z conjugate. When I take the conjugate of a fraction, I have to conjugate both the numerator and the denominator. This is obviously going to look like the effective value of the voltage squared divided by the conjugate of the impedance. So if I know the impedance, I don't even have to know all of the information about the current or the voltage. The magnitudes is all that I need in order to determine complex power. Using these relationships, let's look at what happens for resistors, capacitors, and inductors. So for a resistor, this is going to look like I effective squared times R, or V effective squared over R, because the conjugate of a real number is just the real number. For an inductor, this is going to look like J omega L times I effective squared, or J times V effective squared over omega L. So notice these are positive quantities. So inductors will always absorb complex power. Actually, since there's no real part, we can further refine that and say inductors absorb reactive power. I'm going to write that out here. And on a similar note here, we can say that resistors absorb average power, since that's always going to be positive and not have an imaginary component. Okay. Lastly, for capacitors, we're going to wind up getting negative J I effective squared over omega C, or negative J omega C times V effective squared. So we can say that capacitors supply reactive power. And we're going to use that relationship on Wednesday as we describe the process of power factor correction, which is our last topic in this class. Okay. All right, so that is enough new stuff for you guys for the day. So let me look at your in-class assignment and see if I can offer any help here. Open. So I think this is going to be in-class assignment number 23. For problem 1, I would argue that you can determine the average value of the waveforms literally by looking at them. It's the DC component. So for this guy, the average value is 2. And for this guy, the average value is 7.5 purely by inspection. The effective value is going to be arguably a little bit harder, particularly on this first one, because you have effectively a sinusoid superimposed on top of a DC thing. So you can break it up into two different things, right? So if we had that sinusoid right there, but instead of oscillating between 3 and 1, it was oscillating between 1 and -1, what would its effective value be? 1 over the square root of 2. It's a sinusoid. It's just the magnitude divided by the square root of 2, right? What's the effective value of the DC part going to be? So the effective value is a DC representation. So the DC representation of the DC representation is the DC representation, okay? So effectively, the effective value of this guy here is going to be the square root of 2 squared plus 1 over the square root of 2 squared. We square the effective values of each part and then add them together and take the square root. For this guy down here, you can easily do it using the method that we described in class using the integral. This is the exact same result you would get from using the integral, but much faster. So just as a heads up there, you'll use that in your homework a couple of times. This guy right here is fairly straightforward as well. We want to compute the complex powers if we know certain things. So for instance here, for part A, we're told that the load draws 100 watts of power. What does that mean? The average power is 100 watts. And we're told that it draws it at a power factor of 0.75 lagging. Okay, so we want S in the form of this, specifically asked for it in polar form, right? Well, because our power factor is defined as cosine of theta S, and this is simply the ratio of the average power over the apparent power, we can do a trivial amount of algebra here and find that this should be P over our power factor with an angle of the inverse cosine of our power factor. And we'll do more stuff like that on Wednesday. For part B, we are literally given I and V. So that's just applying the equation. For part C, we are given P, we are given Q, and we are told that we have a leading power factor, which means this must actually be -100. And from there we can go. And then part D is effectively just using this equation again. But we're given the apparent power instead of the average power. Let's see. Problem 3 is a small amount of circuit analysis. Using the alternative relationships that we've developed will get you the results quicker, but if you want to find V and I for everything, you can always use the generic equation. And that's it. So anyway, just wanted to give you guys a heads up about some of the intricacies here because we only have about 35 minutes to do them. So I'm going to stop talking and let you guys take a crack at it. If you need any help, I'd be happy to assist you.